here is number 9 of the problem. We know that the altitude, let's call that D1, is equal to 110 kilometers, which is equal to 110,000 meters. And we also know that the radius of the moon is equal to 1.74 times 10 to the 6 meters. We know this from the chart that they gave us. And previously, I did this one already, and they failed to specify whether or not D meant diameter or radius. I assume diameter since it said D, but evidently it was the radius of the moon, so sucks. And those are the two givens that we know. And we are trying to find the time it takes for the module to revolve around the moon once, which is the period. So there are 3 equations we need to know for this problem. Let's do the net force first. The net force is equal to the force of gravity, which is the universal gravitational constant times the first mass times the second mass over the distance squared. And this is also equal to the centripetal force. And what we're going to want to do from here is then use the equation V is equal to 2 pi r over t, which means t is equal to 2 pi r over v, to find t. So let's get started. From these 2 equations, you can immediately see that there are things you can cancel out. And this mass is the mass of the module, by the way. So M1 is going to be the mass of the module. Great. And M1 is not given in the givens. So we will cancel out M1, and as well as cancel out one of the R's. So we're left with G M2 over R is equal to V squared. So we know that V is equal to the square root of G M2, which is the mass of the moon, over R. Good. Let's migrate to another piece of paper. We know that T is equal to 2 pi R over V. So then we plug this equation into here. T is equal to 2 pi R over the square root of G M2 over R. Now we need to find R. Since the altitude, which is the distance from the surface to the module, is not the distance from the module to the center, nor is the radius of the moon, we want to add the radius of the moon with the distance 1, which is the altitude. And we're going to add those together ahead of time for simplicity's sake. So 110,000 plus 1.74 times 10 to the power of 6 is going to put us at 1.85 times 10 to the times 10 to the 6. So now we have T is equal to 2 pi 1.85 times 10 to the power 6 over the square root of G M2 over 1.85 times 10 to the power of 6. Now it's time for substitution. t is equal to 2 pi 1.85 times 10 to the 6th over square root of the universal gravitational constant, which is 6.67 times 10 to the negative 11, times the mass of the moon, which is 7.36 times 10 to the 22, over 1.85 times 10 to the 6th. And let's see what we get. I'm going to do the top and the bottom separately to just to make sure my answer is correct. So 2 times pi times 1.85 times 10 to the 6th is going to be 1162389.82 by 67. Which will give us 7135.68395. Let's compare that to the answer they gave us. It's slightly off, but considering the magnitude of the scientific notation, I think that should be fairly accurate. I think where I went off was in 3892. Oh, okay. Let me do that again. Yeah, and I get 7132-ish. And so that is going to be your answer.